Alright, so we're just working on a few example problems that might show up on the exam. Here's an example here, right in terms of the heaviside function, u sub c of t, and then we're given this piecewise defined function. Now the reason I'm getting into this is because I want you to remember that these functions are written in terms of off-on or on-off switches, right? And so the on-off switch is u sub a of t, u sub a of t minus u sub b of t. That is, that's time on, that's time off. So in this example, we could write g of t as the function that we're turning on and off times u sub 0 of t minus u sub 1 of t plus the next function we're turning on and off. That would be u sub 1 of t minus u sub 2 of t plus the last function that we're turning on is just function 1, and so that's u sub t of t, u sub 2 of t. Okay, and then at this stage, right, if you were going to write this using the heaviside or the Laplace transform, if you're going to rewrite this, if this were the forcing function, then we could simplify this. Something's happening. All right, sorry about that. That was my browser coming alive for some reason. So I would go ahead and put these in the order, of the heaviside function themselves. So I'd have like a function here for u sub 0 of t. By the way, u sub 0 of t is actually just 1 for us. And then for u sub 1 of t, what do we have? For u sub 1, we have e to the t plus 1, and then minus t squared plus 1. Right, so that's times u sub 1 of t, and then in fact you could go ahead and cancel those ones out, right? So maybe we'll go ahead and rewrite that. There we go, u sub 1 of t plus, now for u sub 2 we have this one that we're adding to this, and this is a minus here, right? So that's going to be minus e to the t, and then minus 1 plus 1 will just give nothing, so that's u sub 2 of t. Good, and so now this is all ready to take the Laplace transform if we wanted to later on. Good, all right. So I'm going to pause for a second and write up the next question. All right, so we're going to invert the transform s plus 3 divided by s squared plus 2s plus 2. And so here's a hint in the denominator. If the denominator does not factor, then complete the square. However, if the denominator does factor, if it does, then factor, and then you would complete the square. Okay, so what we're going to do is that's not complete the square. Sorry about that. That's partial fractions. I was thinking about completing the square. Good. So we're going to complete the square on this one, since the denominator is an irreducible quadratic. Okay, take half the middle term squared, and that's a 1. So if we add 1, we also have to subtract 1. So we have s plus 3 divided by s squared. Oops, let's go ahead and write that in its factored form. Good. And so now I see that I need an s plus 1 in the numerator. So I'm going to go ahead and write that in there. And so that's leaving me with a plus 2, right? So I'll go ahead and make that into a different fraction. And I'll just go ahead and write the 1 here. Good. Now, if this had not been a 1, if this had been like a 4, and I needed, not a 4, let me pick a different number. If this had been like a 3/4 or something, and I need a square root of 3 over 2 here, or 4 over here, right, then I would multiply and divide by that number, right? In this case, I didn't need to because it was a 1, but in general, that's what you would need to do. Good. And now this is ready to invert. And so this is going to be e to the minus t cosine t plus 2 e to the minus t sine t. Very good. Okay, so I'll pause and write the next one. Okay, so next is, let's compute the Laplace transform of the Dirac delta function of t minus 2 times t squared. And you'll notice that there is no formula in the table, no table entry for the Dirac delta times f of t, right? And do you remember the reason for that? That's because this is equal to the Dirac delta function times f of c, and so this is now a constant. And so rather than taking the Laplace of t squared here, that's just going to be 4 times the Dirac. Good. And so therefore the Laplace transform will be 4 times, now I can use the table, let's see, that's table entry number 17. And so that's going to be e to the minus 2s. Good. Alright, so that is my answer for e to the minus 2s. Okay, so I'll pause again and write the next question. Alright, so we're going to solve a differential equation. I forgot to say 0 ICs. That means y of 0 equals 0 and y prime of 0 equals 0. And so before we actually solve this, I think it's a good idea to draw a picture to see what this looks like. And so let's see if we can draw a sketch of that, just for fun. U sub 0 is 1 at 0, right? And then something's going to happen at time, what time? At time pi, right? So at time pi, what happens? Here we'll have 1 minus, so this is going to be a minus, and then u sub pi comes on, so that'll be a 1 minus 1. And so that'll, oops, wait a second. I forgot something. This should be a 2 here. Sorry about that. And so this was actually going to, instead of being 0, it should be minus 1 here. That's what I was looking for. Oops, so that's a plus 1 and a minus 1. Okay, and then what happens at the next value of pi? That'll be 2 pi. At 2 pi, we could write it down. So at t equals 2 pi, what functions are on here? Well, we have our u sub 0, which is 1, minus 2, which came from our u sub pi, that's still on, right? But then we're going to be adding 2 from u sub pi, 2 pi, and so the 2's will cancel and you're back to 1 again. Okay, and then at 3 pi, you can think of these 3 being on, right? And then we're going to be subtracting 2 again, and so therefore we'll have a minus 1 again. And then we're going to be adding 2 in the next round, and so that changes that to a plus 1 again. Okay, and so you can kind of see what's happening here. We're getting what's called a square wave, and the square wave has period 2 pi. And we have a square wave with period 2 pi. But that's an extra thing. I just wanted to make a note of that because my natural period, the natural period for this function, right, is also going to be 2 pi. And so you might anticipate a blow up, right? Good. Okay, so let's see what happens when we try to solve this differential equation. Let me rewrite it down here. Equals, getting sloppy here, plus 2 times the sum, k equals 1 to n, minus 1 to the k, u sub k pi d. Good. Okay, so now with 0 initial conditions, we just get s squared plus 1, which is the, you might notice that's the, what equation is that called? Do you remember? Let's see, that's a 1, so that's going to be a 1 over s plus 2, sum, k equals 1 to n of minus 1 to the k, and that's just going to be e to the minus ks, right? Good. All right. Oop, divided by s. I was thinking of the direct delta function. Okay, starting to lose my memory here. This is bummer, getting old. Okay, so now let's go to y of s. I'm going to go ahead and factor that 1 over s out. So that's going to be 1 over s times s squared plus 1. And then this will just be 1 plus 2 sum k equals 1 to n minus 1 to the k e to the minus ks. Good. And now this we'll have to solve by using some partial fractions. So here, think of this as your h of s, right? Remember how we were doing that before? And so if h of s is 1 over s times s squared plus 1, that's equal to a over s plus bs plus c over s squared plus 1, right? So that means that 1 is equal to a times s squared plus 1 plus bs plus c times s. Good, just to get those out a little bit. And then for s squared, what do we have? A equals 1, 0. Wait a minute. Do I have another s squared in there? I do. A plus b equals 0. There we go, otherwise things would have canceled out on us. S terms. So that was this term right here, and this was this one over here. Okay, and then the s terms, there's no s terms in the front. I guess that's going to be a c equals 0, right? And then constant will be, I've got an a there. Okay, so that's all my constants, but that's going to be equal to 1 instead of 0, right? So therefore, c equals 0, a equals 1, b is minus 1. Good. And so therefore we have all of our constants. And so our h of s, keep that there, is going to be 1 over s minus 1 over s squared plus 1. So little h of t is going to be r1 minus sine of t. Good. And so now can you write the solution in terms of little h of t? Our solution, y of t, y of t is equal to h of t plus 2 times the sum minus 1 to the k equals 1 to n of, now this was e to the minus ks times h of s, right? So the inverse Laplace transform is table entry 13, and that's going to be u sub k pi of t times h of t minus k pi. Good. All right. Yeah, we'll leave it in that form for now. It's kind of fun to draw a picture of this solution, but since we're so far over the time, we'll stop there. Okay, so we'll have another video in the series. Maybe, well, I'll see what happens. See you later.